I'm very glad to be invited to the physics group here. And this month is extremely difficult for me because I'm leading the spacecraft program in Russia. And this is X-ray spacecraft. And main telescope is coming from Germany, Rosita, second from Russian Nuclear Center, and our institute in Moscow. And launch is scheduled for 21st of June. The spacecraft is already on Baikonur, proton launcher is there, booster is there, and if everything will go well, then on 21st of June we will start to L2 point, and then we'll make the X-ray map of the sky. From many points of view, similar to the map of Planck and W map, but in X-rays. And in X-rays, the nature of background is completely different. And we will resolve maybe 50% of the background, and this is radiation from supermassive black holes. And 10% or 5% of the flux is due to clusters of galaxies. And my main difficulty today is that it's necessary every day to sign from here different documents and speak with people, but it is pleasure to give scientific talk at least. Yes, I will speak today, and Juan asked me to talk about CMB spectral distortions, but it's rather difficult to explain them if I will not mention to you two milestones in the life of the universe, which are not advertised too much. In reality, very well advertised is last scattering surface, but not too many people know where in reality real black body radiation can be produced. If it is not primordial, if there was enormous energy release at some moment, can we produce black body today? I will try to talk about this. Okay. This is, all of you know today, this beautiful image of Planck, this whole sky, and it is tremendous picture because you see here, oh sorry, you see here these brightest spots here. They are only 200 micro-K brighter than average sky. When temperature of this radiation is 2.7 Kelvin. Therefore, it is, in reality, it's less than 10 in power minus 4. And these are the brightest spots on the sky. And the weakest blue are also minus 200 micro-K. In reality, on average, this is of the order of tenths of micro-K, these fluctuations. I'm speaking about really peaks. And what is important also, we are living in the universe where baryonic density is extremely low, 10 power minus 7 baryons per centimeter cube, really very low density. And photons, we have of the order of, oh sorry, again I am doing wrong. There is 400 photons in every point, and difference in amount is in really 10 power 9. It is enormous difference in amount of photons and baryons. We are living in a radiation-dominated universe, and very important for us is to remember about redshift, this factor Z. Our universe is expanding, and when it is expanding, wavelengths of every photon also is expanding. Therefore, its energy is shrinking, decreasing. This is a redshift, and everything is going linearly with redshift. Temperature is going like 1 plus Z, and energy of every photon is also going like 1 plus Z if this photon is not absorbed or emitted. And I told you, in every cubic centimeter of our universe, there are 400 photons. I became student in physics of Sunyaev-Zeldovich, who returned from atomic and hydrogen bomb program to the peaceful life. And just after 3 or 4 months after I became student of Zeldovich, absolutely unexpectedly, we got information about discovery of Penzance at Wilson of this CMB discovery. And Zeldovich told me, forget about all problems which I gave you. Now you will work only on this radiation. And he was enormously busy. He had a lot of groups on gas dynamics, on hot plasmas, on low mass nuclei, and many, many other things he was working simultaneously. But there were several other people. My problem was CMB. And I was very happy, and I am very grateful to this person, John Mather, and his team, because several years later, they launched COBE spacecraft. You know, this was a spacecraft where Smoot and others detected angular fluctuations of CMB, but most important were, not for me, and for topic of my talk, were the measurements of group of Fixon and John Mather. Now, John Mather very rapidly after got Nobel Prize for this. I'm showing you the spectrum measured by COBE-FIRAS instrument. And this is spectrum from 5 millimeter wavelengths to 0.5 millimeter wavelengths. First, I can tell you that error bars here are increased more than 100 times, a little less than 1,000. They will be completely invisible here. And their measurements showed that there are any distortions from black body, that at that time when this was measured, it was best black body in the world. Nobody was able to create such black body in the lab, in reality, at that moment. And upper limit to deviations, I was speaking about the same deviations I will talk now, but I had several conversations with John Mather before, and I told him that why is this important and mu distortion is important. You should give upper limit, and to Chuck Bennett. And they gave upper limits, and these upper limits were on the level of 10⁻⁵. And before, I was enormously enthusiastic because Zeldovich was telling me your work is enormously important because there was Berkeley-Nagoya experiment on balloons. Yes, please.
I thought the experiment was done by comparing the CMB to a black body.
Yes, you are absolutely correct. It was done with, with their black body, which they were making in their, yes. But this black body which they did, it was the result, it was interferometer, and in reality it used also the sky in some way. And I can tell you that this black body was better than anything existing in the lab on the ground. You understand? Their comparison. And you're absolutely correct that they had, John, for me now, it is disaster that he involved in another spacecraft, which now is strongly delayed. But with this spacecraft, he demonstrated that he is a really great physicist.
So what they measured actually was not that good, but the ratio.
This was the difference, in reality, the difference between these measurements. And result is enormous, but before, he was grown in the group of Richards in Berkeley, and there was Lange and Taza, and they made this experiment with group of Matsumoto in Nagoya. And their balloon flight detected 25% deviations and demonstrated that black body is, has a lot of additional things. And it's not real black body. And therefore, all these distortions, which I was writing about at that time as a practically childish, they were very important. People thought. And then they were killed, and 25 years it was impossible to observe anything, and every 5 years I was coming to John Mather and was asking him, oh, you know, there is something 10 or 20 times or 100 times lower, and you can detect it. When you will get money for another spacecraft and increase the sensitivity. Finally, he told me, Rashid, nobody gives you money again. Then I asked him, what is in principle possible? And he was 10 years, he was telling me, no, Rashid, nothing. No, there is progress, but it's very slow. And then we met in Venice on the conference in cosmology. I was already permitted to travel abroad. And there in Venice, he told me, Rashid, okay, I tired to talk with you. Today I will tell idea of experiment which will be 100 or maybe even more better. This was future PIXIE proposal. And today, I told you here about 10 power minus 5. People are telling that 100 is easy, 1,000 is difficult. And I had conversation. I like to work with experimentalists because they're very rough people, and they're telling, oh, you are telling the same, tell us. John Karlstrom, with whom we are also very good friends, John Karlstrom told me, Rashid, nobody is interested what you are telling, that we should, for you, make another upper limit. We wish to know what is the bottom, where we certainly will find something. Tell us what is the minimum, and then we will think, is it clever not to try? And then I took two very bright students, and postdocs, these were Jens Hluba and Rishi Hartree, and we made all these estimates. What are these estimates giving? But first, I wish to tell you again that adiabatic expansion of the universe preserved blackbody spectrum established in early times. For example, during electron-positron annihilation. In general, nu divided to T is invariant, and then you know everything, and there will be spectral deviations are possible only if there will be energy release in the universe. And we know that there is energy release in the universe, and there are hundreds of mechanisms which are producing energy. Yes, and as I told you, this very old slide prepared for my talk in Chicago in response to a claim of John Karlstrom. I will speak about only unavoidable spectral features which are predicted within standard cosmological model. I will not mention any, modern ideas and so on. I will tell what people think, what is written in the Bible, okay, which is approved by Planck and WMAP, and therefore I will speak about it. And main things are these two types of spectral deviations, Y and mu. Let us continue. Yes, I will speak about, this is the redshift. We are at redshift 0, and today age of the universe is 13.82 billion years, according to WMAP and Planck, with huge precision. And then when we go in this direction, then redshift is increasing, and time also is decreasing. You see last scattering surface is at redshift in the time 380,000, when redshift is 1100. Universe is much younger, and there is a blackbody photosphere, which I will again show you today. At this blackbody photosphere, if we have had before energy release, it will be any energy release. It will produce Planck, just in our blackbody spectrum. And it is occurring at redshift 2 million, when our universe was very small baby, only 2 months. You understand this? And today, billion of years, and just very soon, when universe was only 3 minutes old, we had electron-positron annihilation, we had nuclear synthesis, and a lot of different things. I will not repeat this 10 times, but I can tell you that if you compute the entropy, then in equilibrium, electrons and positrons have more entropy and energy than photons, just fermions, you add fermions and baryons. And therefore, when electrons and positrons annihilated, you injected enormous amount of energy to the photon gas, increasing practically, I forgot number, 2 or 3 times the amount of energy and entropy on the photons. And we computed with Rishi especially what will be the result, distortions after the blackbody photosphere. According to estimates, I was asking him to write that it's only 100, 10 in the power minus 100, but he wrote 100, 10 in the power minus 109. You know, he believes that precision of our estimates is so high. I do not believe that. It's of the order of 10 in the power minus 100. We cannot see any, even from this annihilation of huge amount of particles, we cannot see the traces. Only neutrino has these traces, and we include this in all our computations. But after these 2 months, whole life, our universe was producing additional energy, a lot of mechanisms. I will tell you about some of them, and there should be the distortions, just should be. Yes, this is another picture, again, of the same, again, electron-positron annihilation, blackbody photosphere. At this time, the matter and radiation, dark matter, have the equality in the contribution to the density of matter. And these are neutrino when they are massless, when they have masses, and what we are having. And here are first stars, and this is the region where dark energy dominated. In these coordinates in the redshift, its dark energy dominated region is extremely small. You see here from redshift, it is up to redshift of the order of 2 or maximum 2 or 3. You see here. Okay. Yes, but story again. In the spring of 1966, my mentor, Zeldovich, asked me to review on the group seminar the preprints of Professor Laser from Harvard, great professional in the dust physics, and Jeffrey and Margaret Burbidge from Caltech. They were very well-known astronomers at that time, stating that CMB spectrum is just the stellar light thermalized by the dust. It was absolutely understandable that all stars existing in the universe cannot produce energy which, even small parts, we know today is less than 1 millionth. Just measured. It's measured by Planck spacecraft, this contribution of dust. But it was absolutely crazy, and I decided to check, in addition, the usual mechanism which are responsible for the blackbody spectrum production inside hot star. If I go to the middle of the star, there also will be blackbody. What people are doing. This is the Rosalind free optical depth. In reality, this optical depth at where the h nu divided to kt is of the order of 3, a little more than 3. It gives main contribution to the diffusion of photons, of energy in photons. And it occurred negligibly small up to time of positron-electron annihilation. 4 times 10 to the power minus 5 optical depth probability to photon, to CMB to be absorbed at redshift 10 to the power 8 in the end of electron-positron annihilation was of the order of 10 to the power minus 5. I came to Zeldovich. Zeldovich was amused. He told me, Rashid, I computed how many positrons are there, but I never made this simple estimates. But I was shocked because optical depth on just simple Thomson scattering was at the same 220 million at redshift 10 to the power 8. It was enormously high. Everything was independent in reality made. Non-transparency is dictated by the Thomson scattering. This was very, very interesting. And then, obviously, I was not reading, Wikipedia was not existing at the time, but my Bible was Landau-Lifshitz books, which I read from, yes, and in Landau-Lifshitz was written that Thomson scattering is the elastic scattering of electromagnetic radiation. Plane wave is coming, electron is in this wave, how it's oscillating, and radiates exactly on the same frequency. No change of any frequency. Obviously, I knew about Compton effect, and Compton scattering is the recoil. You see here, it was done for relativistic photons. Yes, I don't think that it's good to discuss these trivial things, but what was consequence of the optical depths, of so strong optical depths of the when we have electrons? Temperature was decreasing. Near us, temperature is only 2.7 Kelvin. It's cryogenics in reality. And everybody understands that there should be recombination, when photons should recombine. And everybody was doing very simple thing. This is Saha, people were taking Saha equation for ionization degree. It's the same as electron-positrons in equilibrium or electrons and neutral atoms. This well-known formula of Saha. In reality, I was amused. I was in Calcutta giving Bose lecture 10 years ago, and I recognized that Bose's greatest discovery in astrophysics and physics from India, Bose statistics and Saha equilibrium, were done in Dhaka, in college which Brits established in some way in 1917 or 1916, and best people from Calcutta who were unable to get job went to Dhaka and made these discoveries there.
Which is now in Bangladesh.
Which is now in Bangladesh. But Bangladesh is silent, and in India nobody is mentioning this. You know, only in Calcutta people explain it to me. I asked to show me the building where these discoveries were done. And people are telling, no, they came to Calcutta much later than when they became important professors. But all discovery was done in Bangladesh. Okay, I haven't seen other great discoveries from Bangladesh, sorry. Yes, but, excuse me. Yes, and what I can tell you is that everything was fine. I was giving, again, seminar. Zeldovich liked to ask me. He was giving me a question, and when I was coming and explaining him, he was telling, oh, you should give talk on the seminar in Moscow. And I was giving talks, and during this talk in Moscow, in Sternberg Astronomical Institute in Moscow, under Ginzburg, Shklovsky, and Zeldovich, I explained that there is Saha formula. This is it. And this, I don't know why I cannot show. OK, this is Saha formula. You see it. And it gives very fast, narrow, fast recombination around redshift 1,300, 1,400. And everything was fine, but after everything was simple, fine. And then my friend, Vladimir Kurt, who is now in Israel, he asked me, whole his life he was observing Lyman alpha photons. And he asked me, Rashid, but if there is recombination, where is Lyman alpha? And I told him, nobody can see Lyman alpha because it is redshifted 1,300 times. It's unobservable. It's infrared. Nobody can observe at that time. Nothing there. In addition, it is 10 in power minus 30 in the wind tail of black body, there is very small amount of Lyman alpha photons. Again, everybody was happy, even Dim occurred. But after that, I was unable to sleep 2 weeks. I thought only, where is Lyman alpha? It should come, you know, somewhere. And I computed what is the optical depth for Lyman alpha and what is probability of Lyman alpha to go in the very distant wing. And it was 9 orders or 8 orders of magnitude weaker than amount of Lyman alpha which were recombining any moment. This was impossible. I came, told this to Zeldovich that there is great problem. Recombination cannot go as it should in equilibrium. And Zeldovich told me, think about it, read, and so on. And I discovered paper of Kipper in Estonia, who computed maybe 3 or 4 years before the two-photon transition from 2s level in the hydrogen atom. There is 2p and 2s. 2s is forbidden to S1s. Therefore, probability of two-photon emission is 8 inverse second, and probability of Lyman alpha to P1s is of the order of 10 power 9 inverse second. 8 orders of magnitude difference. And then everything became easy. I computed for this 8-second, transition, upper level in equilibrium, lower level, and these are orders of magnitude. This is the recombination. After you take into account this two-photon decay.
Can you explain better what you're saying? An atom which is recombining is most likely to go through the 2s level?
No, it goes to 2p due to the statistical number. 2p is better populated, 2s is less populated, but there is a radiation which ionizes second level and sends second level to the third, photon from the second level to the third, and so on, much faster than it decays. Therefore, second level is equilibrium with continuum, and 1s is out of equilibrium. This beautiful thing, and it is just because, how to say, in the time of recombination, temperature is 3000 Kelvin. Ionization potential is 158,000 Kelvin. You are an extreme wind tail. Therefore, when you go to H alpha line, Balmer alpha line, then probability to absorb from 2s to 3p, for example, is very high. And therefore, they are in equilibrium, and 1s is separated from equilibrium. And when you compute this, these are computations already fresh with Jens Hluba, we are getting this curve, and it is very important and interesting. There are many things. For example, today people are observing 21 centimeter. It is because electrons and protons are colder than, yes, please?
Excuse me, I still don't quite get your explanation. Can you just skip 2s, like continue, go to 2p, then 2p go to 1s?
It is not the case. It is when situation is transparent, you're completely correct. But when optical depth is billions or millions, you cannot go out in from 2p, only to photon.
You can't go out because the photon you emit is then reabsorbed by another atom?
No, photon which is here, yes, because photon is reabsorbed by another atom.
Whereas from the 2s, you get 2 photons.
Yes, and they're going everywhere. But probability is 8 orders of magnitude lower.
Probability is low, but those photons are lost and the other ones aren't?
No, yes, these photons are lost very slowly. Therefore, you just have, you are going from this curve to this, and this is, you see, logarithmic scale. You have huge delay, huge delay. And, but second level itself is in equilibrium with continuum because there are many photons which are taking you and all time sending you up and down.
Second level is with the continuum because it's more than halfway up to the ionization.
Yes.
So the 2 photons
Yes, they go out. They are free. But they are occurring very, very rare. And this is the physics which was done in '68. And then a lot of people were speaking about this, and Jim Peebles also heard about this. He's writing in his paper and computed the same after that and published. Let's go further. Yes, I just wanted to say about Jim. We did this with my late mentor, Yaakov-Zeldovich, with Vladimir Kurt. Now he's completely different, obviously. He's 83 or 84. And this me at that time, I also very different. And this is Jim Peebles, you see. But for me, it is, many things which I will be telling today were in reality done simultaneously in Zeldovich group and here in Princeton. And there was practically no connection in '68, '69, '70. It's interesting. Now I can show you what situation is occurring. This fractional rate of recombination at very high redshift, 1,600, 1,800, 2p, 1s dominates because ionization degree is high, and therefore optical depth in NH is small. And then 2p is working. Then it's only when visibility function, only 2p, 2s, 1s dominates this two-photon decay. And when you go to redshift 600, when again universe become rather optically thin, again Lyman alpha started to work.
Yeah, sorry, I'm asking for some education here. Since Thomson scattering only care about how many free electrons it
Yes.
generates, and both 2p and 1s are both neutral
Yes.
hydrogen.
Yes.
So it doesn't matter whether my neutral hydrogen is in 2p or 1s. And plus the phase space in the first level, 1s is so small, does it really matter whether I
Yes, it's very strongly, it's very important thing. And I will show you in the few next slides. Yes, this formula which we wrote in '69, we took E in power minus tau, tau is optical depth in Thomson, multiplied to d tau over dz, how tau is changing, just to integrate. And this was analytical explanation, and we showed that everything is occurring where this curve has maximum, and where optical depth within there is a visibility function, and when visibility function is from 0.1 to 1, then everything occurs where photons are scattered last time. And after that, they are coming to us freely. And when I showed you that there is a delay, this visibility function moved from here, where it was very narrow because Saha is very fast, to real curve. We moved from 1100, from 1400 redshift to redshift around 1050. Whole visibility function became more close to us. I will tell in a moment why it's so important. Now, because precision of Planck is enormous. Yes. You see, this is a visibility function, which was computed, this reality, and this is Gaussian approximation as I did. This is today measurement from Planck is 1086.5, the maximum of this visibility function. And we computed with Zeldovich at that time. I will show you. It had 1055. Practically 30 years before it was observed, and precision was enormous, but now we are including, and precision is much better. For example, Mukhanov, whom you know, he is very strong. When he heard about this theory, he started to think himself, And finally, he told me why you are not using Planck to measure 2s decay rate. I told him this is the simplest quantum mechanics which I know. And when I was on the fourth year student, Okunin and Termoterasyan were telling me compute 2s, and I was computing. It was easy. It's quantum mechanics. You don't believe quantum mechanics? He told me, no, I believe quantum mechanics, but always good to get experiment. He went to Nobelist Hensch, who is in laser physics in Munich, and asked Hensch what and how, what we can do. And answer from Hensch was the following: I cannot measure it. My precision will be maybe 30 or 40% because it's so slow. I cannot arrange so low density when, you know, this S2 decay becomes important. Then people from Planck, including Jens Hlube, measured it when this visibility for using this visibility function position. And they know now decay rate from Planck experiment with precision few percent. It's not 100, not 99%. It is, precision is, how to say, I think it's close to 0.97, the center. Yes, let's go further. I am very slow. Yes, and why it is important? It is important because when you have this last scattering of the photons, they scatter last time and they come to us. But they are scattering on the moving electrons. And when they are moving on the moving electrons, they have the Doppler from these electrons. They have the potential, therefore these photons change on the variable potential, therefore, because due to the growth of perturbation, they have also changed their energy. And this is the reason why we have these acoustic peaks, because I will show you this here, because there are, this is the sound horizon as function of mass, logarithm of mass, and you see the standing waves in the universe before recombination when there were radiation dominated and there was no growth of perturbation, only standing waves. These standing waves had velocities. Electrons in standing wave had velocities. And we see these velocities today, and we see the potential. We can measure this. This was what was predicted, again, in 70 by, in paper with Zeldovich. And this is what is observed. Sorry, this is what is observed. It is observed. First peak is practically sound horizon of the universe at that time. It is 0.7 degree on the sky. A lot of people, Andre Linde likes to talk about multiverse. I know only one example of multiverse. It is this picture. Because on this picture, I have 360 degrees, and 0.7 degrees is practically horizon at that time. It's sound horizon, but velocity of light is close to c divided to square root of 3 plus contribution from dark matter. It will be of the order of half or 1/3 of velocity of light. And this is the sound horizon. And we see every peak here, this peak is coming from independent universe because they were not sending signal to each other. This was horizon at that time. It's understandable or not? I hope. And therefore, we are observing here 300 to 300 universe. It's 100,000 here. And we are looking today for amount of clusters, because in the cosmic web, in the node of all these 100,000 universes in the intersection of cosmic web, there is now a cluster of galaxies, and we are trying to find all of them, all 100,000 rich clusters of galaxies, because this, again, is information about the early universe. Okay, let's go further. Yes, you see here, I told you already, this visibility function. integral of this visibility function is giving you probability 1 for the photon to be scattered here. This answer to your question. But bulk of the recombinations, it occurred when majority of electrons already recombined, more than 90%. And this is the way where the majority of photons recombining, and this is the spectrum of radiation which coming to us from that time. You see here features due to presence of helium in the universe, and I was so proud to come to Vladimir Kurt and told him, Dima, this is your Lyman alpha. I hope that somebody will find it. It is Lyman alpha shifted by 1,100 times, and it is on in the sub-millimeter band. And this is the prediction of its brightness. This is Balmer alpha line. This is Paschen line, bracket line, and all series which we know, all upper series in the hydrogen atom. Everything, this is, I think we computed 500 and 500. Altogether, this is more than few hundred thousand of levels. All transition, including induced transition and so on. And helium, it is the possibility to measure, for example, such line of helium. It will give you information how much helium was existing in the time when no one star was able to exist.
Where is the center of the black body spectrum in this?
What? Oh, center maximum, 2.7 keV. It is here.
So this is below the black body spectrum. What is the relationship between this spectrum and the black body spectrum?
I can tell you this is here in the Rayleigh Jeans part of it is 10 power minus 7, 10 power minus 6, and where in the maximum it's 10 in power minus 9. This is the minimum which I told John Karlstrom, if you will detect it, this is a lower limit. You certainly should see the recombination, and you will see this recombination from the time which was earlier than time, oh yes, it's here. Then this is visibility function last scattering, and this is from where these photons are coming. It was a redshift of the order 1,350, 1,400, which is in time a lot, 40 or 50,000 years before. Yes. Now let us return to electron, which doesn't change its frequency during the scattering. But if you are an astronomer or you are working in the plasma physics, you know that Landau-Lifshitz books are great, but they cannot write a whole truth in one chapter. This truth is separated and is described in different chapters. Electrons in thermal, electrons in thermal plasma are moving, therefore there is Doppler. There is broadening of the line. This Doppler is very different from our Doppler because this Doppler is the same for every angle of scattering. And for scattering to zero angle, change of frequency is zero. Therefore, we have here cusp. Usually, when I was giving in the beginning these talks, people were not understanding why there is cusp. Cusp is because this is scattering to zero angle. And then it's okay, we have these things, but when you start to think that temperature of electrons are high, for example, in X-ray astronomy, typical temperature is 10 power 7 Kelvin, 5 keV, let's say so. And at 5 keV, electrons are moving with velocity 1/7 of the velocity of light. Therefore, second order Doppler correction is this plus minus. Therefore, it doesn't change energy of photons as a whole. But there is a plus 4 kT divided to meter square, second order correction. And this, again, there is a, how to say, small remark in the Landau-Lifshitz theory of fields, that this change second order of is 4kT divided to the square. Eugen Lifshitz, Evgeny Mikhailovich Lifshitz, was very kind to me always. Therefore, I came to him and told that I got solution why it is 4kT to the square. But I cannot find simple solution because you are writing it's very easy to find. And he told me, oh, Rashid, if I remember all formulae in derivation, which I mentioned in my books or in my papers, I will be crazy. Therefore, go to the cellar. There are books which Russian army captured from the Dresden University, and reading the books of 1912, when physics was finished, everything was done, you will find somewhere this. I went, I spent 4 hours, I found nothing, and this was all. But then I discovered the same formula in the paper of Dirac of 1925, when Dirac was trying to write, to speak about broadening of the photons in atmospheres of the hot stars. And he computed first this term, just up to precision was up to KTE divided to 1/2 to the V to C. He found cusp, but he did not find what is the correction. But he wrote that his term doesn't provide right result for the second order correction. He knew about 4kT. I found 4kT in the lectures of Fermi, which he gave in Los Alamos, which are published. You know, it's everybody knew, but nobody gave. Everybody was telling it's very easy. How I can understand this myself? Yes, this is to show you this change of the frequency 4kT divided to m square. This in logarithmic coordinates. You see the profile, real profile, kernel of integral equation. And this is what people are doing in Fokker-Planck approximation. You see this red, and it's OK. It's working because they specially normalized it to this 4kT exponent. Then everything was fine. Yes. And this equation, Comptonization equation, was found in the Zeldovich group, this simple Fokker-Planck equation of photon gas and electron gas together. N is occupation number of photons, and X is again HU divided to KTE, and there is a density of electrons, and this is Y parameter, which is amount of scatterings, multiplied to KTE divided to m square. Therefore, this factor 4 is enormously important here. And also in these terms. This equation is very simple because this term, dn over dx, and it gives you diffusion of photons and their motion up to in the frequency. Term n is the recoil effect. Photons are going down due to the recoil. And there was number n square. In '68, nobody was speaking that Thomson scattering might be induced. And I understand why and so on, wrote integral equation. Yes, if you include the Thomson scattering also might be included, might be induced, then everything was correct. I came to Zeldovich and asked why you included in this equation n square. And he told me, Rashid, it's simple, because we tried to include Planck, and our equation was not conserving Planck black body radiation. But when we include n square, it was conserving. And we hadn't time to think. We were thinking about hydrogen bomb, because this was the equation which they constructed to see what will be the highest temperature of electrons if they explode hydrogen bomb in atmosphere, and temperature will go up. And they were very afraid, and then there would be detonation of deuterium, and so on and so on. And then, you know, everything will be burning on the Earth. Therefore, they were very careful, and a lot of people were working on decision on the solution of the thermal problem with this equation. Landau, for example, many very well-known Russian mathematicians, including Israel Gelfand, who was in Rutgers later. And I am so fortunate because they were interested only in the energy, in the heating and cooling of the plasma, and nobody was interested in the radiation spectra. And therefore I did this radiation spectra. I think that Landau will solve everything immediately. Yes, I was just, from this point of view, I was very lucky. Let us go further. How I got this factor 4kT to mc square, which gave them immediately the diffusion term of that equation. If there is CMB in rest frame and electron is moving, then electron sees higher brightness temperature in the direction of motion and lower behind it. Everybody understands. This is just Doppler effect. And after that, we can write again formula from trivial Doppler effect and can look what is the radiation pressure force on the electron in the direction opposite to velocity. And it's very simple. This intensity is a function of the cosine of the angle and integrated over cosine. You can do this, and you can get this force finally. You can get this force, and this is very simple formula. And with this, from this formula, if you will now go to the second order in the velocity, if you multiply to v, you have also the work force. I think that children in Russia, children know this in the 5th or 6th class in the school, that force multiplied to velocity gives you the work. You see here, and you are getting term, and from here you are getting easily that change of the frequency per scattering is exactly 4kT divided to mc square. This is solution which I know, which is published long ago, and which we are publishing in every review again. But yes, let's move further. Yes. Now I can tell you that this solution is very important, because with Zeldovich it was easy for us to find first correction to the equation of components in the case when temperature is higher, temperature of electrons is higher than radiation temperature. This is a formula, and it shows that every photon is moving to the 4kT divided to mc square to higher frequency. Every photon. They are moving from here to here, and you see immediately that brightness is decreasing in Rayleigh-Jeans part of the spectrum and increases in the Wien. This is the simplest explanation. It is there. Formula is simple and elegant. And I am very grateful to Jean-Louis Puget, who was PI of the high-frequency instrument on Planck, because I was trying to help. Planck had difficulties. Roger Bonnet was director for science of European Space Agency, was very good old friend. We were going to him together with Jean-Louis, that Planck is important. And Jean-Louis asked me to give frequencies where he will find this prediction on the sky in the clusters of galaxies. And I gave this frequency and told him that the most important is frequency at 217 gigahertz. This is frequency where there is no effect, where two curves are intersect. Here I have negative effect, here positive. We did this, and you see that this is 70, 100 gigahertz, 143 gigahertz. Here effect is 0 to 127. Here technologically was easiest. 353 positive, 545 gigahertz again positive. And they observed clusters of galaxies with enormous potential and with hot gas, with temperatures of the order of with temperatures of the order of 10 million Kelvin.
Is it done cluster by cluster or superposing different clusters?
No, it's every cluster. And now I will show you clusters which are measured with hundreds of sigma, because it's so, these ground-based telescopes and Planck are enormously powerful. May I return? I thought that there was additional picture. No, it's not. Maybe I will show you it later. But I can tell you that now there are thousands of clusters where effect is measured. And in the brightest, people see now shock waves, people see, changes of the density, they see bubbles which are filled by cosmic rays. There is no thermal plasma, therefore there is no this effect, because the electrons are relativistic, they only take in photons and do not return them, and so on and so on. But, okay. Now I will speak about chemical potential. Second solution of the Comptonization equation, stationary solution, is the Bose-Einstein solution. I already mentioned Bose-Einstein and where the statistics was done. And mu is chemical potential here. And there are two constants. For Planck, we need only temperature, and temperature defines both energy and amount of photons. Here, I need to know two parameters, energy density E and then number density of photons, only in the case if I know temperature of radiation or its energy and mu, chemical potential. Only in that case, I will know what and how will occur. This is, at that time in 70, this was a childish prediction what will be there, that on the Planck we will have here the deficiency of the photons, but at low frequencies where Bremsstrahlung and double Compton are working very well, we will get Planck. And this was the spectrum which was predicted and was given to both COBE, FIRAS, and to future spacecraft. Here I should stop for a moment because there are, maybe not everybody of astronomers remember this, but I hope that everybody will remember. You know that we have the Thomson or Compton scattering, and what is it? That there is a gamma photon. This gamma photon is scattered on the electron. There is recoil of the electron, and electron, due to recoil, is accelerated. It is classical description, and if electron is accelerated, when it is accelerated, it should produce photons, because it's radiation and it is there is dipole and so on. Therefore, it is way to get scattering is most important, but this radiation, we have the name for it. Mainly people are speaking about low frequency photons. It's double Compton. We know this, it was. Okay, again, this books on quantum electrodynamics was half of my life on my desk all time. Therefore, double Compton was common thing. And what is today, we know our universe, when we were working in 70s and 60s, universe, everybody saw that there is no dark matter, and on the place of dark matter are baryons in some way. When dark matter appeared and dark energy, amount of electrons and protons in the universe decreased, and role of Bremsstrahlung became, became much weaker than role of double Compton. And at low frequencies, double Compton and Bremsstrahlung absorbed or create photons with this divergence, 1 divided to x squared. Therefore, they are very effective at low frequencies, and they are ineffective at high frequencies. And I will show key thing now. This is how we are producing a black body. And black body, only one way to produce black body is the following. This is Bose-Einstein. this is Bose-Einstein spectrum. And at very low frequencies, electrons, due to Arable, due to double Compton, and due to Bremsstrahlung, keep black body. And after they keeping black body here, there are at higher frequencies, Compton is much stronger, and it takes photons to higher energy, to higher energies. Just they're diffusing due to diffuse term up to here, and then recoil doesn't give them to go too far. This is the physics. And this is the result that if you have enough time, you're producing so many low frequency photons that this deep is decreasing, decreasing, and decreasing, and you are getting black body. This is the situation which we were interested in 1970, and I can show you now that solution, analytical solution, which we found with Zeldovich published in 1970, and this is again exponent, initial mu, and A and K. A, E, and K, A in scattering, Comptonization, probability with this 4 kTe, and real absorption due to Bremsstrahlung or due to double Compton. And this is the result. And finally, there is a solution. This solution gives immediately this condition for double Compton with 2.5 degree here. And this was done just from that solution. Next step was published by Danese and Desozzi. I was interested only with Bremsstrahlung at that time. Yes, therefore there is chemical potential. This chemical potential, we can decrease this mu, and we can do a lot of additional things here. I will not describe energy exchange, but I can tell you only one thing. Now this is black body photosphere, and this is L, spherical harmonics on the sky. All Planck pictures are working up to this, up to L equal 10 power 3, up to 5 arc-minute on the sky. And I'm speaking about the L equal 10 in power 8, 5 orders of magnitude higher. And tiny parts on the sky. It is there invisible, but any energy release at that time will produce mu distortions. Any energy release. I don't care about mechanism, but first mechanism, which is unavoidable, is just the silk dumping. Yes, a few days ago I congratulated Joe Silk because he got Gruber Prize, Cosmology Prize, and I was writing letter 6 years to support him, and every time was my main argument was, I don't know, was it easy or not easy to get this such paper when you're graduate student, but most important is that his name is on the skies for next 40 billion years at least. Therefore, finally he got this prize. I'm very happy. It is good. There is still dumping due to viscosity and thermal conductivity of the sound waves in the photon liquid. Electrons are necessary only to define the mean free path of photons, nothing else. And then you're getting, and spectrum, classical spectrum, which is, you know, Mukhanov is asking me to quote that this is a spectrum which they computed with Chebyshev and predicted this is that spectrum with logarithm, and it is undubbed, which should be. And there is nothing. All energy of these sound waves are in SIMB. And this is 10 in power minus 8 or 10 power minus 9 spectral deviations, which are coming just from this. And this is what people should detect. If the spectrum here is wrong, excuse me.
Let's see, the sensitivity of this PIXIE will be such that they will detect this.
I can tell you I was very unhappy, but experimentalists should be not bright but honest. And I was asking them to tell that they will try to detect and so on and so on. They were telling, no, we still do not have for 5 sigma detection. We need to make device 7 or 8 times better. This is the reason why they still aren't improved. But they should increase, but then price of the spacecraft increases. Therefore,
they detect the other one, the spectrum that you showed before?
yes, it is the same, 2 or 3 factor. It's easier. But here but I can tell you it's question of time. I will tell you, unfortunately, I do not have time. I can tell you that there is enormous progress on the ground. But on the ground, you made it in the observatory. Next day, you go and put it to the observatory. From laboratory, you go to observatory, and you observe. But in the space, you sign a contract, and you have no right to change anything in the device. It's very complicated. But a lot of people are trying now and thinking how to do this. And I am telling you, this is 10 in power minus 8, 10 in power minus 9, depending. Obviously, I can say you, oh, maybe Bukhanov and Chibisov are wrong, and it goes so. Then, or there is additional component, and there will be revolution, you understand me? But today we do not know. We cannot measure this. We measure, Planck measures only up to this. And this is more than 5 orders of magnitude in the scale, in the angular scale.
You're not measuring an angular...
Oh, I am not measuring, but I am getting information about it. I am getting information about what occurred on these tiny things. Yes, and this is in reality what we are doing. We are taking, this is, my colleagues like this picture. K is inverse dimension, this wave number. K here, and again, this where we can do Lyman alpha data, CMB best fit, low everything, what we can go. It is 7 folds. And we can observe spectral distortion from all this region up to here. And it is 17-fold, E-folds. It is enormous how much information is there. We can get from the whole life of universe. We can get information about any energy release. And in the beginning, it will be mu-type distortions, then intermediate I will show you, and here only Y-type distortion, which is already observed. Yes, it's practically similar, black body surface and black body photosphere here, and this is silk dumping. But there is additional, I will tell you in few minutes, if you will not interrupt me, about Bose-Einstein condensation in the universe, which maybe will be interesting for you. Yes, these are the spectra which is possible to observe. Blue is a spectrum for mu distortions, and this is spectrum for the Y distortion. Mainly, how they can, one of the difficulties is that it is necessary to distinguish between them, dust, and so on. People wish to be very careful. Yes, this is a simple linear formula for mu distortion, which is just here is given, easy to use. And if we are in narrow in the region where it is not fully mu and not fully not fully y. In that region, this is the exact computation. Now several groups did the same. It is how you are increasing parameter y and how the spectrum evolves from mu, which is red, to this, which is y, or opposite. You know, this difference. And I only tell you only one thing. Here you are dependent on time. Y is in reality equivalent to time. Therefore, you can distinguish here if this is a particle which is decaying. Then you can find from the type of the distortion, you can say which, how to say, what is the lifetime of the particle which produces this signal. Because you will, if it is earlier, you will be more close to mu. If it is later, you will be more close to y. It's, yes, please?
What physical process could cause a non-zero chemical potential?
Or any process when you inject energy, any process in early enough universe, it will lead to mu. If it is coming to the late universe, it will be y. You just injection energy, and we don't care, is it decay of particle or evaporation of black hole or anything. But we can go and speak in astrophysics, okay? I will explain this detail. Okay, yes, let's go. Now I promise to tell you about Bose-Einstein condensation in the universe.
The point is that after this photosphere story, the photon number is conserved, but you establish thermal equilibrium by scattering, right?
Yes, and thermal equilibrium by scattering, it is Bose-Einstein, because it's conserving amount of photons. It's absolutely correct. Now I can tell you that if we live in the universe, which is expanding, and if I will take entropy for baryons, then this entropy is written here, and entropy for radiation is written here. If it is dark matter, it's also very similar to, in some way, you can include dark matter also. What is important, that if you will look, baryons cool like 1 plus z square. It is like gas with 5/3, with gamma equal 5/3 adiabatic index. And radiation cools down like 1 plus z, like liquid with gamma equal 4/3. Therefore, photons are cooling like 1 plus z, but baryons are cooling much faster. They are non-relativistic. And therefore, you need photons all time, give the energy to radiate. Electrons are taking energy from photons. It is opposite. You do not have energy release. You absorb energy from radiation. And then these two terms, which I told you connected with recoil effect, which is recoil and induced Compton scattering, they are moving photons to lower frequency. They are moving photons to lower frequency, and this is 10 in power minus 9. It also might be detected if there is, but it is 10 power minus 9. It may be 3 times smaller than energy released from the sound waves. Therefore, if for some reason sound waves will not operate at very low frequency, very low scales, then there will be Bose condensation. It's also interesting. Now you asked me what are the 3 sigma, or what is the detection limit. This is Planck and COME cluster of galaxy. COME is measured now with hundreds of standard deviation. All map is there. People resolve a lot of things. I will not show you. On southern sky, people are observing with ALMA, with 64 dishes, all these clusters of galaxies, and they see this, effect there with tiny angular resolution, and then see details on the cluster of galaxies. Yes, I can show you what is observed today by South Pole Telescope and Atacama Cosmology Telescope. With just Y. Red is Planck clusters, 1,200. Blue, somewhere here, are clusters or they deleted Atacama Cosmology Telescope. This is black, is what is today observed by South Pole Telescope, which is in few hundred meters from Ice Cube, from neutrino detector. And you see they detected a lot of clusters up to redshift 2 today. Several clusters are at redshift 2, a lot of them. And this blue, what they are claiming they will be able to detect in 5 years. Because they have now in their focal plane 16,500 bolometers, cryogenic bolometers, working simultaneously. It's enormous. I have pictures of everything. I don't like just to take your time. And these are clusters, masses of clusters, 10 in power 14 solar masses, 10 in power 15 solar masses. And you see this sensitivity is of the order of 5 times 10 in power 13 solar masses in dark matter. People will see this. And they're counting, and I told you every cluster is a node in this distribution in the cosmic web. And we will get this. By this, just by this microwave. And oh, there is, it's very bad because I wanted to show this, how they see these shadows on the sky, clusters of galaxies. And okay, maybe if somebody interested, I will show that picture from South Pole Telescope, which John Carstrom gave me, but told, don't give anybody else. Well, but I have permission to show. Okay, yes, I again show you this picture, and you see that from redshift 2 million, any energy release in the universe, not tomorrow, maybe in 5 years or in 10 years, will be observed. Question is, you know, for me it's important. For younger people, it's okay, 10 years to wait, but this certainly will be measured. People know how, it's only question or to get more money. Spacecraft is bigger, and everything will be done tomorrow, or if there are no money, then you should wait, then technology will be better. Okay, yes, there are many other things which are changing and making situation much worse. For example, these carbon monoxide transitions, we see them everywhere now on this South Pole Telescope and Atacama Cosmology Telescope, sees all this transition and see how carbon monoxide is everywhere. All transitions between this rotational molecule, and there are transitions between equidistant levels. Again, extremely simple quantum mechanics. And you see here, these are just our prediction, what will be all the lines and what will be the flux. It is dust, synchrotron, how, in addition, which spectral distortions will be there. It's possible. This is carbon-2, 158 micron line, which is also very bright in the star-forming regions. Yes. And this I promised you to show spacecraft, which is already on Baikonur. And I can tell you that these guys, because they are also bringing heavy things, they're taller than I am now, but close to me when I was writing these papers. I was at the time 5 centimeters taller. Yes, this is the station, and it is beautiful. This is Rosetta telescope, which promises us to observe 3 million supermassive black holes on the sky and 100,000 clusters of galaxies. Therefore, we have competition, or this ground-based telescope on South Pole and Atacama Desert, or space. And this is, oh, sorry again. Sorry. Yes. And this is Arctic Sea telescope, which is more hard X-ray, for more hard X-rays. It will detect Compton-thick AGNs, which are normally invisible in the soft X-rays. All soft X-rays are absorbed, but hard X-rays can diffuse out, having recoil. we dream to have many objects of this Thomson-thick black hole side chains. This is a situation additional, and I have lists of papers where people are discussing different energy releases in the universe. I can tell only that CMB spectrum is very rich in information about the early universe, late time universe, and fundamental physics. This information is accessible and within reach of experiments, is not too far future. And we know the technique. Question is only money and the line, because there are other groups of astronomers who also wish to get money to observe exoplanets and so on and so on. Yes, I think that I eaten my time, or not yet. Yes, thank you. Yes.